So here's a slide that I was missing last time that states the two key properties of all closed Hilbert complexes. The Hodge decomposition on the first one, and the Poincare inequality in the second one. I just want to, now that I had a chance to write it carefully, go back to Zicheng's question about interpreting the Hodge decomposition. Let me do it in the general case, the interpreting the Poincare inequality. So we have Z is bounded by the Poincare constant times dz. Let me put the superscripts on now. If Z is in the domain of D and the orthogonal complement of the null space of D. And then we wanted to write this in a way we could interpret it more easily. And so first let's imagine there are no harmonic forms. So then we just look up at our Hodge decomposition and we say the orthogonal complement of the null space is just B. Otherwise it's B plus harmonic forms. So it's the range of D, of the previous D. Sorry, hold on one second. Not yet. No, not yet. That's not what I want to do. I just want to look at our complex. We have VK, we have D coming in, DK coming in, and DK minus 1 on the way in. And if there's no harmonic forms, then the null space of DK is equal to the range of DK minus 1. And if there's harmonic forms, we have to add the harmonic forms here. So I'm going to replace that null space of DK with the range of DK minus 1. And since I want the orthogonal complement of it. So these are equal if there's no harmonic forms. And I'd have to add the harmonic forms, so then it'd have to be orthogonal to this and also to the harmonic forms. Let's hold off on that. No harmonic forms, these are equal. Okay, now I use the fact that the orthogonal complement of the range is the null space of the adjoint, so this is D star K. So another way to write the space in the Poincare inequality is that this holds for all Z that are in V, and also in the null space of DK star. And if there are harmonic forms, they would also have to be orthogonal to the harmonic forms. So all Z in here such that Z is orthogonal to harmonic forms. So I can do that in any case. Now if we come over to this case of the curl, so that says that U is bounded by the curl of U for all U and H curl, and they're in the null space of the D star operator, and that's div on H01. So that would be the one that said div U equals 0, U dot N equals 0 on the boundary.
Excuse me, sorry, do you mind if we put down the shade ruler?
Oh, good idea, yeah. These ones. Thanks. Okay, so in general, that's a way to interpret the these spaces of Poincare inequality. Okay, any questions? So then what I did next was define the abstract Hodge Laplacian. I'll wait for them to sit down. So then we define these three different formulations of the abstract Hodge Laplacian. In the first one, we assume that every derivative, every D and D star we throw at U makes sense. So u is in the domain of D, it's in the domain of D star, du is in the domain of D, D star u is in the domain, sorry, D is in the domain, du is in the domain of D star u is in the domain of D. So LU makes perfect sense, and we write down the strong form. In the second one, we don't make as many assumptions on the domain, on the place where we look for u. It's only in the domain of D and D star, and we have this weak formulation where there's only one D and one D star that hits u. And so it's obvious that the strong form implies the weak. Not as obvious the opposite direction is also true. And then in the mixed weak formulation, we give a name to D star u, call it sigma. And we give a name to PHF, call it P. And then we don't need, and we impose the condition that sigma is D star u by using the definition of that, which means we don't have to have any D stars in our formulation at all. Now, the theorem is that in the strongest possible way, these things are all equivalent. So the easy direction is to prove that anything satisfies the strong satisfies the primal and the weak. Now I want to show that anything that satisfies this weak formulation actually automatically satisfies the strong formulation. Okay, so what do we have to do? We have to say if U solves the primal weak formulation, U is actually in the domain of L, and once it's in the domain of L, then we're done, because that means that du is in the domain of D star, so this term can be written as D star du integrated V, and this term can be written as D star u integrated in V. And so we would have Lu inner product V is F minus PHF inner product V for any V, and therefore Lu equals F. So how do we get that if U solves the primal weak form, which means that by definition, so let's write it down here so I can use it in the proof. It means that U is in V and it's in V star, and du dV inner product and D star U D star V inner product is FV, or F minus PHV, FV for all V in that space. How do we prove that, which one do I want to prove in my notes? How do we prove that du is in the domain of D star and D star u is in the domain of D? So how do we prove that du is in V star? And the answer is you use the Hodge decomposition. So let me go back and put the Hodge decomposition up. So the first thing I'm going to do is I'm going to take a Hodge decomposition of F. Which is F is equal to a sum of three terms. A term that's in B, the image of D, harmonic guy, and a term that's in the image of D star. So FB plus, we already have a name for PHF. And actually, so maybe since that's that's a W orthogonal decomposition, this is just the projection of F into B plus the projection of F into H plus the projection of F into B star. And I'll just call this FB and FB star. Okay, so that's our Hodge decomposition of F. And now let's look at V that's in V intersect B star. Okay, so of course B star is contained in V star, so that's an allowable test function in the primal formulation. And let's plug in that test function. And so we get du dV, and well, V is in B star, so D star of B is equal to V is equal to 0. And here, this is FB plus FB star, and the FB part is orthogonal to B star. This is an orthogonal decomposition. So that part drops out, and we just get FB star V. And that would be for all V in V intersect B star. Now, we also have du dv equals the same thing, FB star V, for all V in B. Why? Well, FB star is orthogonal to B, so this is 0. And dv is 0 if V is in B, so this is 0. And we also have it if V is harmonic, because FB star is orthogonal harmonics, so that's still 0, and dv is 0 for harmonics. Okay, now we have the three components. Now look at the second Hodge decomposition. Those are the three things that add up to all of V. So we've proven that du dv equals FB star V for all V in V. Well, call du tau. That says tau dv is FB star V for all V in V. That's the definition of tau being in the domain of D star, and D star of tau being F star B. So this is exactly the definition of du being in the domain of D star, and D star du is equal to FB star. So what we've proven is if you have a solution to the primal weak formulation, even though you didn't assume that du was in the domain of V star, it is in the domain of V star. So this is again what I was saying in this theory. Somehow you don't have to argue with any deep estimates to show something has more regularity. It comes from how you're defining regularity in terms of domains. Okay, so we've proven it. If you have a u in the primal weak form, then the u actually satisfies du is in V star, and of course similarly D star u is in V. It's completely symmetric in V and V star. D star u is in V. And so it solves the strong form. So this means those things all together means u is in the domain of the Laplacian. So any solution of the primal weak forms in the domain of the Laplacian and satisfies the strong form. Okay, is that clear? Sounds awfully quiet in here. I used two things. I used the Hodge decomposition, as it's written there, and I used the fact that tau is in the domain of D star, and D star tau equals Q if and only if tau dV equals Q V for all V in the domain of D. That's the definition of tau being in the domain of D star, and D star tau is equal to Q. I applied this with tau is equal to du. And Q is equal to FB, the Hodge component of V. And I verified this equation using the primal weak formulation by looking at the test functions V, doing a Hodge decomposition of the test function V, and checking each of the three pieces. Two of them were trivial, and one of them was the primal weak form. Therefore, I have du is really in V star, even though I didn't assume it at the outset. I get this one. This one comes from the primal weak formulation. The next equality is because both sides are 0. If I take a V that's in B or is in H, it's orthogonal to anything in B star, because we have an orthogonal decomposition between B star, B, and H. So they're all orthogonal to each other, so there's 0. B star is orthogonal to B. It's the top line of that equation. B star, B, H, and B star are 3 orthogonal things. So FB star is orthogonal to the other 2 pieces of V. There's the piece here, and there's the 2 pieces here. It's orthogonal to those, so that gives us 0. And D kills B, because D of D is 0, and B kills H, because H are the things that D is 0 and D star is 0. That's the definition of the primal weak form. U is in V and V star, and the test function V is in V and V star. No, look, what I do is I'm trying to prove this. I'm trying to prove du dv equals fb star v for all v and v. That's what I need to prove. That's the definition of d is in u is in the domain of d star. So I say, well, I'm going to take v and I'm going to break it into 3 pieces. Really, it's really 2 pieces. One is v intersect b star, which is the 3rd component. That's also known as zk. That's also z perp inside v, because b star is z perp. And then the other part is the z part. Actually, the z part, which breaks up as a b and an h, but actually I can treat them together. Okay, so it's v is equal to z plus z perp inside v, no doubt about that. For the part that's in z, this is 0 because this is orthogonal to z. And this is 0 because z is the null space of d. So for the part for v in here, it's just 0 equals 0. For the part in here, I got by taking that same test function, it's in v and it's also in v star, so it's allowable in the primal weak formulation. And when I put it in there, I got this equation. Okay, I think maybe you just had too much for lunch. So where are we in terms of equivalence? We've shown that the primal weak form and the strong form are exactly equivalent to each other. Both. I'm not doing anything deep. Nothing is deep. Everything followed from definitions. Yeah, that's what I thought. Right? So that's why I can do it in an abstract Hilbert space framework. And that's pretty much in the nature of this. So if you're in, I went through my life teaching courses, teaching the Laplacian, and say, well, a solution of Laplacian is a C2 function, so Laplacian u equals f. We call that the strong form, happens at every point. But then we introduce this weak form with the space h1, and the strong form implies the weak form. And the weak form, well, if the solution is smooth enough, then we can do this. And somebody once proved that it's smooth enough on this domain and that. This isn't like that. In this one, you introduce the strong form. The strong form implies the weak form, and what's more, the weak form implies the strong form. They're completely equivalent, just from the definitions. Okay, now I have to show it's also equivalent to the mixed form.
Can you play around without using the Hodge decomposition to prove?
I can't. Literally, I can't. I think this is... The first several times, it took us a while to realize this, and then we finally, gee, this Hodge decomposition is incredibly powerful. You can even prove this. So you can try it. I can't. Well, but the Hodge decomposition is take the space, you have a closed subspace. The Hodge decomposition is orthogonal decomposition to Hilbert space. You know, mathematics is you take a few trivial assumptions and you start reasoning, and it gets complicated. No, strong form, that's exactly the point. The strong form means being in the domain of the Laplacian. And once again, I think I said this, but I'll say it again. Why is elliptic regularity trivial when we know it's not trivial? It's because the regularity we get is the final u you get belongs to the space of functions whose Laplacian is in L2. We don't identify that as being some other Sobolev space or Basov space or something like that. So it's obvious that if you solve Laplace u equals f, where f is in L2, then u is in the space of functions whose Laplacian is in L2. You've rechanged the definition, so elliptic regularity is a tautology. Okay, so now we still have one more part of the first theorem, that if you have the mixed weak formulation, then you solve either the primal weak formulation, well, that's the one I'll show, which is equivalent to the strong formulation. So in the mixed weak formulation, it looks formally weaker yet, because all we do is assume that U is in V. We don't even assume it's in V star. And we have to prove it's actually in V star. So I want mixed weak formulation implies primal weak formulation, which we know implies strong formulation, which we know is equivalent to this. So we need to show, we know U is in V, and sigma is in V, and P is in H, and we want to show that U is also in V star, and the primal weak formulation holds these equations. So we look at the first equation of the mixed weak formulation, which is that sigma tau minus d tau u is 0 for all tau in V. That is the equation, but it's also exactly as I pointed out before, that's exactly the definition of the statement that U is in the domain of D star, and D star U is equal to sigma. So, in fact, although I didn't say it when I wrote down the primal weak formulation, the mixed weak formulation. Where is the mixed weak formulation? Am I going the wrong way? There's a mixed weak formulation. Although it's not part of the way I stated it when I wrote down, you immediately have from this first equation that V is also in V star. And maybe I'll just stop here. The rest is all very simple, so you can fill it in. From the other two equations, you get that V, which is in the domain of V, and U, which is in the domain of V and V star, V by assumption and V star by looking at the first equation, then satisfies this formulation here. Okay, so we can, what we've done between going these formulations, two different ways to say that U is in the V star. One is to say U is in V star, and the other is to write down the definition of what it means to be in U in V star, and that's in terms of V. Okay? With me? Okay, now I want to actually do something. I want to prove that the mixed formulation has a unique solution. So I want to prove that for any F in W, there exists a unique sigma in Vk minus 1, U in Vk, and P in Hk, such that we have a unique solution to that thing. And I'm going to do that using the standard tool that we use in finite elements to show that a weakly posed problem has a unique solution, namely the M-soup condition. So remember, if I have a bilinear form, let's say on some Hilbert space, bounded bilinear form to R, let's keep it really easy and make it symmetric, although you don't need that, but it is in our case. And we have a bounded linear form on X, so X is a linear F is a linear operator from X to R. Well, it's an XR, so of course it's bounded. And then we define the operator L from X to X star by BUV is LU applied to V. for all v in x, where that's the pairing of x and x star and x, right? And then to say that L from x to x star is an isomorphism if and only if we have the if soup condition, and the if soup condition says that for all v in x, there exists a non-zero u in x such that buv, well, first of all, there exists a positive constant such that buv is greater than the constant times the norm of u, norm of v. That's the if soup condition, right? And this all, and again, this is another trivial just from the definition results, but very useful. Symmetric, that's why I wrote symmetric. Otherwise, I have to do it in both orders. Okay? And I'm going to apply that to this problem here, where the bilinear form, well, I'll add these all together. That's what you do when you have a system. You add these all together. And so it's one bilinear form in which the test function is, trial function is sigma up, and the test function is tau vq. And I have to show for any tau vq, there exists a non-zero sigma up, such that this sum coerces all the norms. And that will give me existence and uniqueness. And so here it is. We're going to use mixed formulation, and there's the bilinear form B, which is the sum of all those equations, sigma tau minus u d tau. And then actually I took the difference sign, put a minus sign in front of the second one, minus sigma c sigma v minus duv, and then the last one minus pv. Well, these three terms are the middle equation, and then the last one minus uq. Okay, maybe we should go back. So I have these two terms, then I subtract these three terms, and then I subtract the last term. And the reason for using subtraction is because now this is a symmetric bilinear form. And so our goal is given, I did it the other way. So given, it's symmetric, so it doesn't matter. Given the sigma up, I have to find the tau vq, such that b of sigma up tau vq is bigger than the product of the norms. Okay, and we're going to do this, and the only constant that is going to enter this is something that depends on the Poincare constant. And what that means is not only am I going to get that L is an isomorphism, but I'm going to get the norm here, the norm of L inverse as a linear mapping from x star back to x is equal to gamma inverse. So we're going to have a bound on the norm of the inverse that only depends on the Poincare constant. Okay, and so I'll do this. So it's just a small calculation. First, let me give you the idea. Why am I choosing these crazy looking test functions, tau vq? Where did we come up with that? And here's the idea. Let's write down the bilinear form. So we have sigma tau, d tau u, d sigma v, du dv, pv, and uq. And I've given sigma u and p, and I have to choose tau v and q. And I have to control, I want this to be greater than, and I have to control sigma, not only in the w norm, but also in the v norm, so sigma and d sigma, and similarly u and du. And I have to control v p. There's no dp because it's harmonic. So actually, very often the way you prove this, and I'll prove it here also, is I prove that for all u, there exists a v such that this is greater than gamma u squared. and v is less than a constant times u. That's the same thing, because then this would be greater than gamma over c uv. So I have to, given my sigma up, I have to choose my tau vq so that this course is the square of this, and tau v q is less than a constant times sigma up. That's the way we usually prove in soup condition. So then I have to look at this thing and say, well, how am I going to control sigma? How am I going to control d sigma? How am I going to control u? And I have to control all these 5 terms. So a lot of them are easy. It's obvious how to control them. How am I going to control sigma in the w norm squared? Well, I take tau equals sigma. So to get this term, I'm going to use tau equals sigma. And that'll get me this term. How am I going to control d sigma? Well, that's pretty easy also. I have a d sigma here, so I'll take v is equal to d sigma. Negative. I'm going to eventually take a linear combination of these with, if I put a minus sign there, with positive coefficients. But, okay, how am I going to control u? Well, that's not as easy. I could go over here and say, well, I take d tau equals u, but that I can't take d tau as u because u might not be in the domain in the range of d. So this will help me control u, but it won't control it completely. This will also help me, but q is harmonic, so this will only get a tiny piece of u, the harmonic part. So this one is a little bit of a trouble. I have parts of it, but not all of it. du is a piece of cake. I take v is equal to u. And p is a piece of cake. I take v is equal to p. So really the only trouble is how am I going to control u? Now, what am I going to use? I'm going to use the Hodge decomposition. So u has a d part. It's a d of some rho, plus a harmonic part, plus a d star part. Actually, did I want to call it d of rho, or I'll try to follow the same notation that I used before? Yeah, plus, let's call it u of b star, ub star, where this is in b star, which is the null space, the orthogonal complement of the null space of z. And this is in b. And since this is in b, it's d of some rho, where rho is in v. Okay, well, the harmonic part of u is easy to control. I'll take q is equal to the harmonic part of u. That's harmonic, and this will give me the harmonic part of u squared. So that'll give me a good term. The d rho part is easy because I'll take tau is equal to rho. And then I'll get d rho u. Well, that's the b part of u integrated against u, so that's the b part of u squared. So I'll get the norm of this d rho squared. So what's left is the b star part of u, where there's no part here that seems to be helping us. Okay, for that we use the Poincare inequality. The Poincare inequality tells us when this zk, that's the b star part. So for anything that's in b star, the norm of it is bounded by the norm of d of it. So ub star is bounded by the Poincare constant times d of ub star. By Poincare. But d of ub star, well, if I take d of u, the first two terms drop out. They're in the null space of d, d rho and dph. So this is the same as d of u. So to bound the b star part of u, it's enough to bound du. And du is a piece of cake. Du we bounded by taking v equals u. Conclusion. By choosing tau, combinations of tau is sigma, v is minus d sigma, v is u, v is p, tau is rho, and q is phu, we'll get all the terms we need to bound, and using the Poincare inequality. And the question is, how do you combine them so they all come out with the right signs and so forth? And that's where you fiddle around, and you end up with this formula here for the test functions. There's these two possible taus we have to take, sigma and the rho that came in, and there's these various possible v's we have to take, u and d sigma and p, and for q, what do I think? I need to take q as minus p to cancel another term. So now let's write it all out and see that it actually works. Is the idea clear? So what I'm trying to do now is I take b and I take sigma u and p, and I plug in those guys. Sigma minus 1 over Poincare squared of rho and minus u minus d sigma minus p, and minus p plus phu. And I write out what it is. So we need the definition of B, which is at the top of the slide. So this gives me sigma squared from that term with sigma, and minus 1 over C2, the Poincare constant squared, times sigma rho. Okay, that's the first term. Then I have minus u d tau. So minus u d sigma, and plus 1 over c squared u d rho. Then I have minus d sigma v. So minus d sigma and then three terms. The first one is minus minus, so plus d sigma u, plus d sigma squared, plus d sigma p. And then the last term, so no, not the last, so what did I do so far? I've had d sigma v, then I have minus du dv. So minus du, and when dv gives me three terms, one of them is plus du squared. One of them is plus du d sigma. One of them is plus dup. That takes care of the, no, sorry, it's du dv. So du du is du squared, du dd sigma, that's 0. And du d rho, that's dp is also 0 because p is harmonic. And then I have minus pv, so minus p, and then these three terms, which is plus pu, plus p d sigma, and plus p squared. And finally, I have minus uq, so that's plus up and plus uphu. So I've really done this laboriously. I've written out every term, if we get it. Now, a number of these drop out. I already pointed out we had a d squared, so that was 0. We had a d onto a harmonic guy, so that's 0. Here we have a harmonic guy versus a d. Harmonic guys are orthogonal to d, so that's 0. What else? Here we also have a harmonic guy orthogonal against a d, so that's 0. Now, this is u with phu, so that's phu squared. What else? Here we have a ud sigma, with a minus sign, and here we have a UD sigma with a plus sign. And did these really come in with the same sign? Or did I make a mistake? This one came from, that one came from where? From minus du, no? That one came from minus PV, so that should be minus PV, plus PU. And this one came from, something seems wrong. Did I make a mistake? Let me just do it very. What's that? My Q should be positive P plus UH, and that would change only the last two terms. Oh, positive P minus UH maybe. So maybe if I take P is, Q is P minus PHU. Then that would switch the signs of these two terms. The last term should be a plus. I have a minus there.
No, you did it wrong the first time, actually. When you wrote the...
Okay, let's get rid of this term. Which is the value I should take for Q? Is it the one I wrote down here?
No, the one you wrote down there.
Here, I should take this one. And so the last term is minus UQ. So that's minus UP. And plus UPHU. And this minus UP cancels out this plus PU. And I got the right sign. Okay, so wrong Q over there. And now we're virtually done, I think. So let's collect what I haven't crossed out. Oh, we have another simplification here. D rho is the B part of U. So this is PBU squared. So that was a good term. D rho is equal to B part of U. So what we have left is we have sigma squared, which we wanted. We have d sigma squared, which we wanted. We have the B part of U squared, which we need. We have the H part of U squared. We have du squared. We have P squared. So what we're missing is the B star part of U, for which we'll use Poincaré, that's already bounded by the du part. And do we have any bad terms here? Yeah, and we have one term that doesn't have a nice sign, which is this one. And that one we have to hide in the others. So this is equal to sigma squared. Well, I'll put the two sigma and the d sigma together. So sigma and the v norm squared, I guess. And okay, well, let's deal with this term here, the sigma rho term. So we have sigma rho is bounded by norm of sigma times the norm of rho, and the norm of rho, yes. That is a point I have to make. Here I said rho was in V, and so d rho is the B part of U, but of course I have many choices of rho, because then I could add anything in the kernel of D, wouldn't affect it. So I'm going to take rho to be orthogonal to the kernel. In other words, it's going to, remember this is at the previous level, vk minus 1. So I'm going to take a rho that's orthogonal to the null space of D at the previous level. I can do that because it doesn't matter what it does in the null space of D. So rho also satisfies a Poincaré inequality. Rho is less than Cp d rho. So sigma rho is less than sigma rho, which is less than Cp sigma d rho. So we have this bad term that doesn't have a sign on it, but fortunately I divided by 1 over Cp squared, so this is 1 over Cp when I put that there. And so this whole thing is greater than sigma squared plus d sigma squared plus pbu squared plus phu squared plus p squared. And did I forget anything? Plus du squared. And then minus one bad term. And that one bad term, we bounded over here by 1 over Cp sigma d rho. D rho is PBU. Did I still, I'm still hoping that I got my constants right. I thought I did that over here. I had, maybe I should stop now. I had this. Okay, and well, so I bound this by 1/2 sigma squared plus 1/2 Cp squared d rho squared. And yeah, okay. So I bound that. So I have the sigma p is bounded by 1/2 sigma squared and Cp squared over 2 d rho squared. So I can subtract off 1/2 sigma squared and 1/2 Cp squared d rho squared. And there was a 1 over Cp squared in front of it. No, I took care of the. This term? Oh, this one. This one, this PBU, which is this one here. So I should have had a 1 over Cp squared here. Now, okay, so then I'm going to, this term here I have to divide by 1 over Cp squared, right? So actually I did this wrong, okay. I put probably the Cp squared in front of the sigma term here and the 1 here. And then when I divide it by 1 over Cp squared, I get a 1/2 in front of the sigma squared and a 1 over 2 Cp squared here. So this is 1/2 sigma squared and 1 over 2 Cp squared here. And then this term can hide into this term, and this term can hide into this term. And so the whole thing is greater than 1/2 sigma squared plus d sigma squared plus 1/2 1 over 2 Cp squared PBU squared, and all the rest of the terms, PHU squared and P squared and DU squared. So I have all the terms I need with some positive constant in front of them, except I still don't have the PB star part of U, but that's bounded by the DU part by Poincaré. So this whole thing is greater than the norm of sigma plus the norm of U plus the norm of P, all squared, and with some constant that depends on the Poincaré constant. And of course, the choices I took are all bounded. Tau is bounded by sigma and rho is bounded by du, and so forth. So it's a bounded choice that gives me control over this. So maybe I shouldn't have worked out every detail. It's the kind of stuff that we do all the time, taking these choices as test functions and fiddling around to get the constants right. I can't use Bretzi's theorem because I don't have a saddle point problem. I do have a saddle point problem, but I do have a saddle point problem, but it's not of the Bretzi form like this. You can't write it in block form like that. No, you can write it in block form like this.
But you suppose you don't do the kernel first. You just treat it as the harmonic function. Forget about that.
So forget harmonic. There's no harmonics. Okay, take the case of no harmonics. So you have something like, no, it doesn't work. You have minus d tau u, and you have d sigma v, and then you have du dv. Well, it's not a singular perturbation, it's a primary term.
Or what is the analogy with this mixed method with the Romeo-Thomas? What is the kind?
So if we wrote a variational form, the mixed variational form, which maybe I should have done, but there's only so much time, I guess. The mixed variational form of this, with, say, no harmonic forms, it's easy to add in the harmonic forms, is sigma u is a critical point, which turns out to be a saddle point, of 1/2 the norm of sigma. This is it, I'm writing it down. Minus d sigma u plus du dv, du squared. That's, and then minus fu. This has a half, and then it's minus fu. So in other words, if you call this functional L of sigma u, so sigma u, so we get that L of sigma u for the exact solution is less than L of L of tau u, and it's greater than L of sigma v for all tau and v. So it's a true saddle point. But it has this extra term here. It's not a saddle point with a 0 here.
When you do the Romeo-Thomas business, what is the...
When you do the mixed method for the Laplacian, the standard one, that's the case of n forms. And in that particular case, this last term drops out. So that case can be handled by Bretzi's theorem. None of the other cases can be handled by Bretzi's theorem. If you do the opposite end, the 0 forms, then this is the only term that doesn't drop out, and you get our standard method du dv equals fv, grad u grad v equals fv. That also can't be done by Bretzi's theorem. The only case that can be done by Bretzi's theorem is the n forms case. So I'm not just rehashing Bretzi here. Marcus. Well, I'm not going to prove the Bretzi condition. I'm not going to prove stability Hidway. Well, if you're proving the Bretzi,
You don't need a
okay.
regularity to prove this.
If you're proving the im-sup condition for the mixed Laplacian on the continuous level, you don't need regularity.
You don't need that, but
You need the fact that every L2 function can be written as the divergence of an HDiv function. That's pretty easy to prove. You just need that Laplacian goes from h minus 1 to h1 for that. You don't need any higher regularity to prove that. Okay, so I don't know. I mean, it depends if you're into mixed methods whether you followed this whole discussion. But this weak variational problem, the weak mixed formulation, is exactly the statement that you have a critical point of this functional here with a quadratic sigma squared term here. By the way, there should be a minus du squared here. Minus du squared here. So that it's quadratic decreasing in u, or du, it's quadratic increasing in sigma, it has a cross term. And if you write down the Euler-Lagrange equations for a stationary point of this functional, it's precisely the mixed weak form, and it's a saddle point because this is a minus du squared and this is a plus sigma squared. And now the Bretzi theory is a theory for proving the im-sup condition for things of the form that break up like this but without this term. But this doesn't apply to that, so you have to go back to Babushka's basic im-sup that applies to any bilinear form, which is what I did. No, it only applies if the operator is very simple.
you don't argue with God about
No, so you could have the following theorem. You could ask the following theorem. Suppose you have a positive definite bilinear form here, a mixed bilinear form here, and a positive definite form here. You don't have a simple Bretzi's theorem. It's not true. If this form and this form are related in some simple ways, it's true. Like if this is basically a multiple of the identity or something, then it's true. But it's not true for any positive definite operator. I mean, if it was, what is Bretzi's theorem? I go back to the matrix case of Bretzi's theorem, A, B transpose, B, 0. Okay? Then you define a space which is Z is the null space of B. And Bretzi's theorem says that this matrix is invertible if A is positive definite on Z and if B is 1 to 1. Then this is invertible. Now you got a simple theorem that says when any matrix of this form is invertible. I mean, every matrix is of this form. Every symmetric matrix is of this.
C is positive. Is there any, sometimes the Bretzi's theorem can be applied. I guess it cannot be applied here.
It can't be applied here unless you know something about similarity of the eigenspaces of A and C and how C breaks down with respect to Z and things like that. So it can't be done in a simple way. So the Bretzi theory is probably a consequence of this theorem, but not the other way around.
Okay, then follow-up question. Can you do this with the Stokes without using Bretzi's theorem? Do this trick?
What trick?
Well, I mean, the Stokes, you prove the Stokes operator is well closed by using
I don't think the usual thing you prove with Stokes, certainly not with the Dirichlet boundary conditions, easily fits in this context. So I don't know a quick answer to that. Okay. Questions?
For your comment about the strong solution is not equivalent to the weak solution. When you're talking C2, of course not. But if you're looking at Gelfand triple, the strong form it is equivalent to the weak form.
What does that mean? So I have 801 L2 H minus 1.
U equal to F, they are looking at is from H1 to H minus 1. If you're looking at this is a triple space, H1, L2, and H minus 1. The strong form is exactly equivalent to the L2.
You mean by the strong form the mapping from H01 to H minus 1?
H1 to the H minus 1, yes.
Yes, that's completely equivalent.
Right, right. So when you, yeah.
But here I have, but here I have a smaller space. I have the domain of the Laplacian.
Right. This is a different framework. Then you're talking about it when the solution is smooth enough, then that's U belongs to H2. That is much more deeper. Right. So that is the theory.
That's right. But so here, the way I defined weak formulation and strong formulation, they're not obviously equivalent. The way you're doing it, they're obviously equivalent. You're defining them to be the same thing. Right? You're defining, so what's obviously equivalent is BU V equals FV and LU equals F. Those are obviously exactly equivalent in two different notations, bilinear forms. I didn't do that. I did one LU equals F, which was not defined via a bilinear form, and then one by a bilinear form, and I had to show that the solution to the one with the bilinear form was actually in the domain of L, which was not by definition. So there was some work involved. Okay. Now, one thing that should have come up very clearly in these proofs is that there's a real close correlation or relation between the solution of the abstract Hodge Laplacian and the Hodge decomposition of U and the Hodge decomposition of F. And actually, that came up in our proof of equivalence, and let's make it very precise. So we know that if we solve the abstract Hodge Laplacian, then we've solved the problem d star u plus d star du plus phf is equal to f. We solve this is equal to f minus phf. Maybe I put them in the other order, and then it's exactly our Hodge decomposition in the order that we've written it. So remember, when we solve the problem, this is in the domain of D, and so this is in B. And this is in D star. And this, of course, is in H. So this is the Hodge decomposition of F. If LU equals F, this is the Hodge decomposition of F. So solving the Hodge Laplacian is simultaneously computing the Hodge decomposition of F. Lots of other ways to say that. One way is to define the solution operator. Define K from W to the domain of the Laplacian. This is a bounded linear operator. And it's just given by K of F is U, where LU is equal to F minus PHF. So solve the Hodge Laplacian and call the solution. So U is just Laplace inverse, where it's understood that you first have to subtract off the harmonic part of F and normalize it by U as orthogonal harmonic functions. So this problem has a unique solution, and we call that solution K of F. So that means that the Hodge decomposition is, the first term is d star kf, the second term is phf, and the third term is d star dkf. Another way to write that is this is the L2 project, or the W projection onto B. And this is the W projection onto B star. You want to project onto the space of D's, you first solve the Hodge Laplacian, and then you take d star of the result, which is in the domain of d star and gets you back into W. And that's PB of F. Now actually the next, so I'm moving down these bullets here. We've hit the first bullet and the second bullet and the third bullet. The fourth bullet is another one of these regularity results. And again, it'll show how easy regularity is in this context. So suppose F is better than just in W. It's actually in V. So you can take dF and still end up in W. So then you can compute kdf. You can solve the Hodge Laplacian with df on the right-hand side. And the statement is, the answer is exactly dkf. So the claim is, if f is in V, then dkf is in the domain of the Laplacian, and d star plus d star d of dkf is equal to df. I don't have to subtract anything harmonic because df is a d, so it's orthogonal harmonics. So let's see how this works. So dkf being in the domain of the Laplacian. Well, kf is in V and in V star, and dkf is in V star, and d star kf is in V, because that's what it means to say kf is in the domain of the Laplacian. So dkf at least is automatically in V star. That one we get for free. Now dkf is certainly in V because it's in the null space of D. It's certainly in D. The range of D is in the domain of D. It's in the null space. So we have dkf is in both V and V star. And this equation here says, let's see, dk. So now what else do I need to show? I need to show that d star of dkf is in, let's see, I take dkf. I need to show this is in the domain of D, and I need to show d of dkf is in the domain of d star. This one is automatic because it's 0. So the last thing we have to do is show that d star dkf makes sense. And I guess we should probably write down the statement of the Hodge Laplacian here. So let's see. So we have dkf dv plus d star kf d star v equals f minus phfv. See, am I doing the right thing? I'm trying to show that, right. So I do it just like when I proved the equivalence theorem. Now let me take a v that's in b star intersect v as a test function. And then this term will drop out because I have a d star of it, and d star of b star is 0. So I get dk f dv equals f minus phf v for things in here. What am I trying to prove? And what about if, oh, I think let's see, we already proved this, didn't we? Maybe I'm reproving. From the fact that, so from the fact that L of kf is equal to f minus phf, then we have that d star we have d star d of kf is the b star part of f. P b star f. And what am I trying to prove? I'm trying to prove that, okay, so this quantity here, d star dkf, well, we know that d star dk is the projection onto b star. So we're trying to prove the projection onto b star of f is in v. That's this equation here. Okay, and let's write out the Hodge decomposition of f. It's that f is equal to the projection onto b star of f plus the harmonic part of f plus the projection onto b of f. And we're trying to prove this is in the domain of d. This is certainly in the domain of d because it's harmonic. This is certainly in the domain of d because it's a b, so it's in the range of d. And this is in the domain of v by assumption. So this is in the domain of d by subtraction. Okay, so I probably should have said it in a different order, that if you take in f, you do its Hodge decomposition. If it's in the domain of d, that means also the b star part is in the domain of d. Okay, since the b star part is in the domain of d, the b star part is d star dk, so that means d star dk is in the domain of d. And so in that way, I've shown that dkf is in the domain of the Laplacian, and then it follows easily. Then all these multiplications make sense. The d of d goes away, and we get d star dkf is. So then we get, I guess I should write that down. If f is in the domain of d, we have I'm trying to prove that d star plus d star d of dkf equals df. That's what I'm trying to prove. And I've now proved that all the domains make sense, so I can apply all these operators like this. Well, here we have d squared, so this is d star of dkf. But I could also write this as d star d plus d star of dkf, because d squared is equal to 0. So sure enough, we have the Laplacian of dkf as df. maybe we can see it just as well from here. Here's the Hodge decomposition. Hit both sides with D. We're allowed to because every term, this term's in the domain of D. These two are, so this one is also. So we get df. This term goes away. This term goes away. And we get dd star dkf, which is the same as dd star plus d star d of dkf. Oh, it's the same proof. Okay, so now, by the way, you sort of just remember these rules, and these give you a calculus, which makes it easy to work. So one rule you remember is that dd star k is just the Hodge projection onto B, and d star dk is the Hodge projection onto B star. Another thing you remember is you can commute d and k as long as the thing you're operating on is in the domain of D, so it makes sense. There's, of course, a similar relationship that you can commute d star and k. D star k f is the same as k d star f if f is in B star. So you can commute those as long as f is in V star. As long as that d star f makes sense, you can commute those. And now comes a useful application. Show that this theory applies immediately to some other problems other than just these Laplacians, curl curl minus grad div and the scalar Laplacian. So let's suppose f is in B. So it happens to be in the range of D. And let's solve the Laplacian. So we have dd star u plus d star du equals f minus phf. So given any f and w, we can solve the Hodge Laplacian and get this equation. But if f is in B, it simplifies. Because f is in B, this part of its Hodge decomposition is gone. And then we have the B part and the B star part of it. But this part is also gone. Because f is in B, this is the projection into the orthogonal complement B star. So the Hodge, if you happen to have data that satisfies this condition, then the Hodge Laplacian just becomes dd star u is equal to f. Now, I can't replace the Hodge Laplacian by the equation dd star u equals f. The solution of Hodge Laplacian satisfies this, but lots of things satisfy this because anything in the null space of D star could be added to this. So I should add on a condition to this that U be orthogonal to the null space of D star. Then that would determine U uniquely because I've gotten rid of the null space here. The null space of D star, the orthogonal complement, is, well, this is a calculation that we've now done a million times. The null space of D star, the orthogonal complement, is the range of D, which is also the same thing as the null space of D, plus the orthogonality of the harmonic forms. If there's no harmonic forms, the range of D is null space of D. Otherwise, the range of D is a little bit bigger. So, so I have to, sorry, this is an element of the orthogonal complement, which is the orthogonal complement of the range, which is the orthogonal complement of null space intersect the orthogonal complement of H. Because the range is the null space plus H. No, sorry. What did I do here? It's amazing how often I can get confused at this point. The null space of D star, there's no, Right. The null space of D star is the orthogonal complement is the range of D. The range of D is the same as the null space of the previous D if there's no harmonic forms, but if there are harmonic forms, it's a little smaller. The harmonic forms is the orthogonal complement of the range in the null space. Okay? So this condition, U should be in the null space of D, that's du equals 0, and U should be orthogonal to harmonic forms. These two together is the same as saying U is orthogonal in null space of D star. Let's remember this so I don't confuse myself every time we have to write it down. Okay, so this problem is a well-posed problem because I got rid of the null space. So this is what we call the B problem. Given f in B, find U such that d star U equals f, du is equal to 0, and U is orthogonal to harmonic forms. And the solution is unique because we put in these extra conditions. And the solution exists because the solution is just, there exists a unique solution, and it's just U is equal to KF. Just solve the Hodge Laplacian with that particular data, and you've solved this problem. Of course, you can't solve a B problem, d star U is equal to F, unless F is in the range of D. Otherwise, it certainly would be impossible. We should probably have an example on the board of this. Let's do it for 1 forms. Very close to the Maxwell equation. K is equal to 1 forms. So then D acting on U is curl. Well, this one is not. Let's do it on 2 forms if I want it to look like Maxwell. Otherwise, it'll look different. We'll go back to 1 forms later. Then for the 2 forms, the D star is the curl with the 0 boundary condition. U cross N is equal to 0. So this, and the D going from the 1 forms to 2 forms is also curl. So we're solving curl of U is equal to F. And du is equal to 0 says div U is equal to 0. And there's an essential boundary condition that U is in the domain of D star. So that says U cross N equals 0 on the boundary. And U is orthogonal to harmonic i's. So this is the curl-curl problem. And you can't solve it for any F. You need F that's in the range of curl. Which means it's divergence-free. So given a divergence-free F, orthogonal harmonic functions, solve curl U equals F, div U equals 0 with a boundary condition. This has a unique solution because the solution is also the solution of curl U minus grad div U equals F. U cross N equals 0 on the boundary, div U equals 0 on the boundary, and that's what, and U is orthogonal to harmonic forms, and that's what we called the Hodge Laplacian problem for 2 forms. And this extra term drops out because div U is equal to 0. So that's the closest way you see the connection between Maxwell and the Hodge Laplacian. Maxwell is the Hodge Laplacian applied to problems. Well, of course, Maxwell, time harmonic Maxwell also has a lower order term here that we ought to put in. If we did this, we'd be solving time harmonic Maxwell equations. And that is just Hodge Laplacian applied to the B part, to a special data F. As a matter of how to do these things, I believe if you want to solve this problem, solve this problem. Because we're going to have a beautiful theory for this problem. And if you gave good data, automatically you'll solve the system div U is equal to 0. This is only on the boundary here.
That means you want to solve a mixed problem.
And we'll use the mixed method to solve this problem.
That means the traditional theory wrong.
Well, there are about 50 different methods to solve Maxwell in the literature, and some of them are good and some of them are not good. And in my opinion, almost all the good ones are equivalent to doing this. Let's go to the K is equal to 1 case. then it would be given f, which is a gradient, solve grad div f is equal to, grad div u is equal to f, and curl u is equal to 0, with some boundary conditions which are probably u dot n is equal to 0 on the boundary. And harmonic forms would come in, one forms in this case. One way to think about this problem, since the gradient is a very simple operator, if we write f is equal to gradient of some capital F, then after we adjust for the constants, we're really solving minus div u is equal to capital F, and curl u is equal to 0, and the boundary conditions. So this is, of course, a very common problem in fluid dynamics and other sort of situations, div curl problems. If you want to solve a div curl problem, sorry, this is not div. Yeah, that is div, yeah. If you want to solve a div curl problem, then my suggestion is take the gradient of the f, call that little f, and solve this problem, but don't solve this problem because this is equivalent to Hodge Laplacian. So solve the Hodge Laplacian with gradient of little f, and that'll solve a div curl problem. So all the problems that are closely connected to div curl problems are in this situation. And then there's the B star problem, and maybe I won't write everything down here. Well, since I'm doing this at the sort of primal strong form level, B and B star, you just can always reverse it. So it's the same story. Can do the thing, you can do this thing over here. And that would be a Maxwell-like curl-curl problem at one form level, and that would be a grad div kind of problem at the two form level with different boundary conditions. I think we did this, didn't we? Yeah. Okay, so I will end it here. Any questions?
Yeah. Little bit, so you proved that the primal form is equivalent to the mixed form, right?
Yes.
Well, the existing primal form is trivial, I suppose. The Hodge Laplacian is the
Right.
part of that. So the solution of there would be a solution of the mixed form.
Right. So you might say, why didn't I use the primal form to prove existence of uniqueness instead of the mixed form? Because I'm going to, in the next lecture, talk about approximation of Hilbert spaces on the discrete level.
That is,
And-
they are not equivalent on the discrete level. That's what we discussed. It's related to
Well-
the question I asked you earlier, to the lunchtime.
the difficulty, it sort of comes in there. The difficulty is, let's see, how do we say this? The difficulty is, you see, when you get to the discrete level, the D star operator is a very shadowy thing. It's not very well understood how it behaves. So there is something that's equivalent, because the discrete Hilbert complex is a Hilbert complex, but the primal form is difficult to understand. So you would get a mesh-dependent, an H-dependent, maybe I should answer it after we look at the, why don't we wait for this? So what you're going to see is the stability of the discrete problem is going to be entirely handled by applying that theorem that we had. And that wouldn't be
Primal formulation, whose existence is straightforward, so you can just do this. But this cannot be carried over to discrete.
well, it's carried over, but the result that you get is not so easy to interpret.
So then the,
What's that? Well, so we're going to take the Hilbert complex, we're going to take the finite dimensional subcomplex, and we're going to look at its abstract Hodge Laplacian. It has a primal form and a mixed form, and they are equivalent to each other. But the difficulty is Yes, so one way to say it is that D star H, so we're going to get a DH, which is D restricted to the subspace. So DKH is DK restricted to the subspace. And then we could prove a theorem about DH, D star H, plus D star H, DH is equal to F, about this abstract discrete Hodge Laplacian. But this D star H, the dual is some sort of global operator that doesn't tell us too much. So I'll try to make this clear when I talk about it tomorrow. Okay, any other comments? Okay, thank you. So we have another talk that's